Let's get started. It's my great pleasure and honor to introduce Maurice Herlihy, who doesn't really need an introduction. He's very, very well known for seminal work on multiprocessor synchronization and many other things. He's got, because of this work, a large number of prizes that will take too long for me to go and enumerate, but you can easily find it up on Wikipedia. And he's a member of the National Academy of Engineering. He's an ACM fellow, graduate of M.I.T, graduate of Harvard before that, and really needs no introduction.
Well, thank you. So what I'm going to talk about today is a history of an idea. So what I'm going to talk about today is the history of a scientific idea. I'm going to start at the beginning, when this idea was invented for purposes that had very little to do with its ultimate fate. I'll tell you what the idea is and what the original purpose was. I'll talk about where that idea is today. And then I'll talk about what I think is the most interesting aspect, which is that whenever you provide people the ability to do something, they're going to take it and do absolutely weird and unexpected things with it. And so I'll talk about all kinds of interesting applications of this idea to areas that nobody foresaw at the very beginning. And I think these are perhaps the most interesting ideas to pursue if you're looking for an underdeveloped research area with some low-hanging fruit. Okay, so our story starts in 1993. Now, looking at you, I can see that most of you probably don't remember 1993. So let me give you a kind of brief introduction. So these were the guys who were in charge. The hottest hardware at the time was the Intel Pentium. Not the Pentium 2, 3, otherwise qualified Pentium, but it was simply called the Pentium because at the time that's the only Pentium there was. In software, the hot thing was something called the World Wide Web, which had just been invented. And there was something called a browser that was invented by a bunch of physicists. Computer scientists never invent this sort of thing. This was done by physicists. And there was a kind of controversy at the time because all the smart money knew that this web thing was a passing fad, and like pet rocks that would come and go. Now, there was also the year that Elliot Moss and I wrote a paper on transactional memory. I'll tell you what that is in a moment. It was published in ISCA. It was clear that it got in by the skin of its teeth, in the sense that I've never had a paper accepted that had such hostile reviews. And our shepherd, I think, must have been the person who was the most negative about it on the committee, because he was very tough with us. But it improved the paper a lot. But it was still a kind of controversial paper at the time. What's the basic idea? Well, first off, let me warn you that because of time constraints and the need to kind of stay on the message, I'm going to give you kind of a simplified version of the idea and a simplified version of the technical issues. Everything I'm going to tell you is true, but there are lots of second-level effects you could argue about. And there's some controversial issues that I'm going to not spend too much time on. But most of what I'm going to tell you is reliable. So back in the day, most concurrent systems weren't really that worried about concurrency. So the simplest way to deal with a system that sometimes had sharing going on was to put one big honking lock on the whole thing. For example, the Solaris kernel at one point just had a single lock that protected absolutely everything. Now this has one big major advantage in that it's hard to get it wrong. If everybody knows you need to acquire the global lock before doing anything dangerous, then even relatively unskilled programmers can write programs that work. But of course, this has the problem that in a world where we actually have real concurrency is completely not scalable. And so what we really need to do is we need to get more concurrency out of these systems. So a natural approach is to take your big monolithic lock and break it up into small blocks called fine-grained locks. Now, I teach a course, and I've written a textbook on how to do things like this. And one thing that you learn if you sit down and try this is that it's really hard. Companies like Microsoft and Oracle are finding bugs that have been latent for decades involving the use of fine-grained locks. So it seems like a sensible approach, but in fact, it's really hard to get this right. The other big problem with locks, which people don't talk about all that much, is that the relationship between a lock for concurrent data structure and the data structure itself exists mostly in the mind of the programmer. And it manifests itself usually in the form of cryptic comments. So this is an actual comment from the Linux kernel. Now, I don't actually know what this means either. But I know that if I were trying to modify this device driver, I would be very, very uneasy. You know, it was probably, being part of Linux, it's probably written by some Finnish teenager in the 90s. Who knows whether it's still true? Who knows if it was ever true? But basically, locking relies on programmer conventions to a degree that is hard to justify for real, serious systems. I think the weakest link in locks has to do with compositionality. So the very first thing that we tell freshmen when they take our introduction to computer science classes is, no, you don't have to write your own cosecant program. We have libraries. And the great thing about these libraries is you can call the sine or the square root or the cosecant program any place you want, and you'll get the right answer. You don't need to be an expert in Taylor series, numerical stability, any of these things. You can build up complicated systems on top of lower level abstractions. And conventional locking and monitors and all of these old school kind of synchronizations are not compositional. Think of it this way. The recommended way to build something like a highly concurrent queue is you can put lots of little locks on the inside of the data structure. Now what I want to do here is I want to remove an item from one queue and put it in another one. This is a pretty simple thing. But I want to make sure that this is done atomically. I don't want to see 2 copies of the item. I don't want to see 0 copies of the item. I want to make sure that anyone looking at the system sees that the item is either in one queue or the other. This is a very sensible way to write programs, because if things can either vanish or become duplicated, then it might be hard to build your complicated system. And in fact, this is nearly impossible in languages that claim to support concurrency, like Java and Scala and other monitor-based languages, because the locks are hidden inside the object. It's considered good programming practice to call a method, and inside the method, it acquires the lock, does its business, and then releases the lock. But if you want to do an atomic transfer, you want to lock one queue, lock the other queue, do the transfer, and then unlock them both. And the only way to do that is by exposing the locks, and once you do that, you've given up all hope of having a modular, maintainable software system. So the problem is that, I have to change the colors, locking isn't compositional. And the one thing that we typically demand of our software systems is that they should be compositional. So I want to contrast the old school approach of doing synchronization with locks and monitors, which has all kinds of other complicated issues that I'm not going to go into, but are kind of referred to here, with an alternative approach based on transactions. Now, everyone in systems knows this dark secret, but nobody likes to talk about it, that all of the important ideas in systems were originally invented in the database community. It's true. They were mostly invented by the people working on System R in the 70s under Jim Gray. And the idea that we're going to shamelessly steal here and repackage is the notion of transactions. Now, the IBM people, when they wrote their tech reports like this, they wrote it in IBM database jargon, which, as far as I can tell, is not an Indo-European language, because nobody can read it anymore. Nobody understands it. You don't boot something, you IPL it. You don't have disks, you have DASDs. You know, it really is like Sanskrit. Which means that people like me can steal these ideas and make a decent living by repackaging them in modern English. So, what's a transaction? Well, a transaction is simply a collection of code that appears to happen atomically. It's instantaneous with respect to everyone else. Transactions in multicore tend to be what are called optimistic transactions. So what happens here is never mind the kind of arcane syntax here. What this says is try to do this sequence of operations atomically. If it succeeds, then you're done. If it doesn't succeed, then it comes back and says, sorry, everything you tried to do has been wiped out. Would you like to try again or try something else? And this is the basis for optimistic transactions. It's also something that's used a lot in certain kinds of database synchronization. But here we're concerned with multiprocessor synchronization. Now, from the point of view of concurrent data structures, I'd like to suggest that a programming methodology and an approach to constructing programs based on transactions is a much more scalable, rational, compositional way of doing business than old school locks and monitors. And this is, in some sense, the motivating idea behind most of the work on transactional memory. Now, of course, that wasn't our original motivation. Our original motivation was we just wanted to do lock-free data structures more efficiently. But over time, it accumulated this ideological fervor that I'm presenting here. Now, there is a problem here that is common to all kinds of optimistic synchronization approaches, which is optimistic synchronization doesn't work very well if your optimism is misplaced. So typically what you're trying to do is to apologize rather than ask permission. So you go ahead and you do something, and then afterwards you go around and check and say, is this okay? If it's okay, you're done. If it's not okay, then you go back and start over again. And as long as you don't have to roll back your computation very often, this is a good idea. But if you have in-memory transactions with transactional memory, there are a number of reasons why your transactions might fail. So your transactions might fail because they're too big. So technically the way that hardware transactions work is that your read and write set have to fit usually in your L1 cache. IBM's version, it can be L1 and L2 cache. But still there's a limit on how much data you can work on. On modern programming languages, it can be hard to figure out how much data you're actually using. So if you write a C program, then you can make sure everything is aligned and figure out how big your data structures are. But good luck figuring out what a just-in-time compiler is going to produce. So there's a problem that you don't really actually know how big your transactions are going to be. Another problem is that if your transaction is too long, then you're going to take a timer interrupt, and the operating system is going to clean out your cache to do something, and then your transaction will never succeed. So if your hardware transaction runs for too long, that won't succeed either. If you're trying to take legacy code and make it transactional by stuffing it inside a transaction, it could be that somewhere deep inside your square root routine, it's executing some kind of I/O instruction for some reason. You know, libraries do astonishing things. And modern hardware transactional memory are limited in the machine instructions you're allowed to do inside a transaction. And finally, if you ask the engineers at Intel, under what circumstances will my hardware transaction commit, they'll say, we won't give you any guarantees. It's all best effort. Why is this? Well, normally your transaction should commit, but what if you take a transaction look-aside buffer miss at the same time you take a page fault, and so on. And our lawyers advise us not to say anything about these situations. So in the end, you can't ever guarantee that a hardware transaction will actually commit. Okay, so these are that's the basic idea, why we're interested in transactional memory. That's also some of the limitations on hardware transactional memory. Now what I'm going to do is I'm going to go back and give you a little bit of the story of how this idea developed over time. So this is a graph of the citations for that paper. Now most papers, if you graph them on Google Scholar, the citation will peak 1 or 2 years after the publication appears. Then, so it'll go up, people read the paper, and then they kind of move on to other things. This is kind of an anomaly because you can see for about a decade, this got practically no citations whatsoever. And then starting around 2004, it started getting a lot of citations. And this graph was made about 1 or 2 years ago, so you can kind of extrapolate from then on. But it's highly unusual that any paper would lie dormant for so long and then suddenly receive a bunch of attention. So how can we explain this unusual behavior? Well, we can go to Google, and Google provides a service which is an enormous amount of fun, and don't try it because you'll waste lots and lots of time. But they go through and they index all of the books they've scanned, and they will tell you the frequency of any phrase that you give them by year. So here I plotted transactional memory against multi-core processor. And as you can see, the number of citations goes, it's almost perfectly aligned. 2 things. The main point is that nobody cited the transactional memory paper until 2004 because multi-core processors weren't really a thing until 2004. So what we did back in 1993 when we came up with a better way to do lock-free data structures is we're basically putting fins on your faster-than-light travel spaceship. Nobody cared about this because there weren't really any concurrent systems. Once there were concurrent systems and people realized that they had a problem programming them, then they hunted down the paper and it started getting some attention. A few other things that I learned are transactional memory is also a term used in a certain kind of transactional analysis, which is why there are a small number of citations down at the tail. And multi-core is actually a kind of a fiber, which is also why there are citations going back to the 1960s for the word multi-core. Okay, so one thing that has happened with transactions is they moved into programming languages. So each of these languages and probably a dozen more obscure ones have either the notion of transactions baked into the language, or they have libraries that provide transactional model of synchronization as an alternative to locks and monitors. The one that's probably the most influential is that this is going to be part of the C++ standard. If you download the GNU compiler, you already get what amounts to software transactional memory extensions. So you can put in all of these double underscore keywords and write your programs using only transactions. You can do that today there's a proposal to make this part of the actual mainstream C++ language. So whenever you think of C++ as a programming language, it's clear that once something gets into the C++ standard, it will never go away. And so that implies that from a programming point of view, transactions are here to stay. Transactions are also available in hardware, so the Haswell chip and its successors provide hardware transactional memory. IBM System Z, Blue Gene Q, and one other all also provide hardware transactions. They all provide slightly different models. So the IBM version is somewhat more elaborate, and you can do fancier things with it, but it's also somewhat slower. So that says that once a feature has made its way into the i86 architecture, then also it's here to stay. You know, it's like a virus. It'll never go away. And so both software transactional memory in the form of programming languages and hardware transactional memory in terms of architectures are firmly embedded. Whether this is a good idea or not, you can figure out for yourselves. Okay, so what I'm going to talk about next are a series of recent papers that have taken hardware transactional memory and done kind of unusual things with them. So the kind of standard way of using transactions is to say, well, let's take a program that uses locks and replace critical sections with transactions. There are reasons why sometimes this works well and other reasons why sometimes that's harder than it looks. But what I'd like to focus on here are really the more unorthodox uses of hardware transactional memory. And I think there are there are many other areas where you can also use hardware transactions in a kind of unorthodox way. And if you're a grad student looking for a research area, then this is the part where you might want to pay attention. Okay, so locks. Now, I started out by denouncing locks and saying that they had all of these problems, you should replace them with transactions, but really that's kind of simplistic. And you can't demand that people get rid of locks anymore. Then you can say, well, the advent of higher level languages means we should get rid of C. You know, locks are basically here to stay because there are situations where that's really what you want. And sometimes this discussion is kind of mischaracterized as saying, well, you know, that locks and transactions are actually fundamentally opposed to each other. That we should that one side or only one side or the other can end up ruling, and the other one has to fade away. But really, I think it's more like transactions and locks can be used together to do things that individually they couldn't do. So one example is something that we call lock teleportation. This is a paper that I wrote with an undergraduate at Brown recently. So the idea here is one of the classical approaches to doing concurrent data structures is something called lock coupling. So the idea here is that we want to go through, for example, linked list. So you lock one element of the list. Now you want to progress down the list. What you do is you lock the next element while still retaining the first lock. This is sometimes called hand-over-hand locking for obvious reasons. Then you release the first lock, get the second lock. So you're always holding one lock when you acquire the next one, then you release one, then you get the next one. And this is classically used in the B trees and things like that. It has pretty mediocre performance in most multi-core architectures because you have to do memory barriers each time you acquire the lock. You can't have overtaking and so on. But on the other hand, it's often better than having a monolithic lock. So the idea behind lock teleportation is that we're going to use optimistic hardware transactions as a way of semi-automatically increasing the performance of this locking scheme. So we start out in the same way we did before, where the thread, represented by the little chip icon, is holding a lock on one end of the list. And now it starts a hardware transaction, which reads all the way through the list until it gets to the end. And it can do this because the meaning of a hardware transaction is that it's like you freeze the world, and then you have a snapshot you can read all the way through without observing any concurrent activity. Actually. And then you, inside the transaction, you release this lock, you acquire that lock, and then you commit the transaction. And to the outside world, it looks like you teleported the lock from one part of the list to a part that's far away. And in particular, you did not need to acquire and release all the intermediate locks. You didn't need to do memory barriers at every intermediate stage. Now, the one fun thing here is that you remember that hardware transactions are all optimistic, which means they might abort at any time for any reason. And so what you do here is, if I get greedy and I try to teleport really far away, and it either takes too long, or it overflows my L1 cache, or I have a synchronization conflict, or the hardware is just not in the mood, and it aborts my transaction, then I can start over with a smaller transaction. And I could do a kind of a standard exponential back off strategy, which is semi-automated. And in this way, I can have the teleportation automatically kind of adjust to the conflict level, to the load, to the cache size, to the architecture, and so on. So this is an example of something where locks and hardware transactions can be used to help one another out. And in combination, you can do things that you couldn't do individually. We have some performance results, which I'm not going to dwell on. But the takeaway is that there's a kind of a more general principle here, which is that if you have any system that's based on atomic state transitions, you can use hardware transactions to kind of short circuit these. And so instead of doing something where you acquire a lock, you do a transition, you do memory barriers, and do all of these expensive things, you can use hardware transactions to do the transitions, and you can think of the lock as kind of a placeholder. So I use the transaction to move from one state to another, perhaps leapfrogging intermediate states. And then I can use the lock to freeze the state of the object, or at least enough of the state of the object, in between hardware transactions. And I think this is kind of a general principle that can be applied to lots of other data structures. So one of the, there's an enormous literature on clever synchronization algorithms, clever locking algorithms. And particularly when you get into readers-writers locks, then there's lots and lots of material. So some of my colleagues at Oracle Labs discovered that there was this ancient read-write lock algorithm that had a bug. How could a bug survive for 20 years? Well, in a day and age before people actually had multicores, nobody really implemented it or tested it, and nobody really cared, whether it worked. And so when this was re-implemented many years later on a big Oracle multiprocessor, they discovered that it was mysteriously crashing and deadlocking and so on. And then they finally found the error. So they went through and did something, they replaced some of the more complicated parts with hardware transactions. Now the code using hardware transactions is much, much shorter and much simpler than the original code, because the problem with most synchronization architectures is that you can use compare and swap to modify a single word. And if what you really want is to modify multiple words, then you need to introduce levels of indirection. And you need to play games where you set one bit and set another bit and unset bits. And this is exactly where synchronization algorithms can go bad. because people are very bad about informal reasoning about these sorts of things. If you replace it with a hardware transaction, really what you're saying is, I want to change this state to that state, and it's much easier to get that right. But on the other hand, it's not really a magic bullet, because as I mentioned, hardware transactions are optimistic, their best effort, they might not actually succeed, so you need to have a fallback. So what you can guarantee is that the main fast path is going to be faster and simpler, but you need to have a fallback in case your hardware transactions are not in the mood to ever commit. And that reintroduces a lot of the complexity of the original algorithm, this time fixed. But all it does is it takes the complexity out of your main path. And it's not as if you can go in and just slap transactions around complicated code and have it work. You still have to reason very carefully about what you're doing. So the takeaway here is that instead of simply replacing locks, you can use hardware transactions to implement locks and related kinds of synchronization primitives. So almost any kind of synchronization primitive you want to do could, at least in principle, be improved by putting hardware transactions inside, because it makes it simpler, it makes the correctness more evident, and most of the time it will make it more efficient, but not always. Another area where hardware transactions have been used is in memory management. So memory reclamation for highly concurrent data structures is difficult. Now, by memory reclamation, I'm thinking of malloc and free, explicit calls to memory management libraries, not automatic garbage collection. Now, the problem is that if you have monolithic locks on everything, then malloc and free are actually not all that hard to use, at least not significantly harder than for sequential programs. But if you have highly concurrent programs, then there's a problem that I might unlink a block from a list at the same time that another thread has a pointer to that in a local variable. And I have to be very careful that I don't recycle it while that pointer is still alive. So there are a number of solutions that have been proposed to this. Perhaps conceptually simplest one is reference counting. So there are lots of concurrent reference counting algorithms in the literature. Nobody actually uses reference counting for this because it's incredibly expensive. Every time you have to increment or decrement a counter, that's a compare and swap loop, and that's just hugely expensive. Another approach is what's called quiescence. So every now and then, everybody guarantees that they've taken all of their pointers, these hazardous pointers that they have in local memory, and they've either cleaned them out or they write them out to a memory where everyone can see them. And so if everybody periodically quiesces, all you need to do if you want to decide whether to reclaim a block of memory is you wait until everybody has quiesced at least once, and then you check to see whether they still have a pointer to it. And typically they don't. So quiescence has the advantage that it's very efficient. There are a number of papers that have experimented with this, and it's awesome performance, but it's highly non-fault tolerant, because if one thread is delayed and you don't hear from it, then you can't ever recycle any memory ever again until that thread wakes up and tells you what pointers it has squirreled away. So it performs really well under kind of normal circumstances, and really terribly if you have asynchrony or any kind of scheduling anomaly. There's a pointer-based so-called hazard pointers, and related algorithms are more robust. They don't require threads to keep taking steps. The basic idea behind hazard pointers is you publish a list of all the pointers you might be using. And if I'm deciding whether to recycle a memory block or not, then I look at everybody else's published hazard pointers, and I refrain from recycling anything that's published as a hazard. This works moderately well, but it has the problem that you have to do a lot of memory barriers. And particularly if you're traversing a linked data structure like a list or a tree or a skip list, you have to do a memory barrier at each traversal step, which is very expensive. So last year in a Eurosys, my colleagues and I wrote a paper talking about how you can use hardware transactions to fix many of these problems. So the idea here is that the problem with reclamation is that we don't know what pointers the other threads have squirreled away on their stacks and registers. So if there was some way to peek into stacks and registers, we would know whether it was safe or not. And what Hazzard Pointers basically do is they write out a superset beforehand. What acquiescence does is you wait until somebody tells you. But if we could somehow atomically look at these things. So the idea here is, well, if you take your concurrent application and if your application were a memory transaction, then it would be okay. Because I could just go ahead and free something that looked like it was going to be free. If there was a conflict, then the transactional machinery would catch it and would roll back either the freeing or the application, and would guarantee that everything is consistent. But we can't take large applications and turn them into memory transactions because the data footprints are too big, they run for too long. So instead, what we need to do is we can take the application and transparently chop it up into a sequence of memory transactions. So basically, we take each basic block and execute it as a memory transaction. Before the start of the transaction, we write the registers and stack and what's changed in the stack to memory. And this guarantees in a relatively painless way that we can do a memory reclamation without delaying anyone and without being vulnerable to slow processes. And of course, we can pick the transaction size adaptively, a little bit like the teleportation. If we get too greedy and we make our transactions too big and they start failing to commit, then we can chop things up into smaller transactions. And in the limit, we fall back to using locks, which has terrible performance, but then that never actually happens. So the takeaway is that you can take innocent applications that don't know anything about hardware transactions and transparently chop them up into transactions and guarantee certain invariants that you wouldn't get if you kind of ran them in your native form. The particular invariant that we are using here is publishing pointers to potentially hazardous data and inhibiting premature reclamation. But you could imagine that there might be other kinds of invariants that you would like to depend on. And I think that this is also a kind of a general technique that hasn't really been explored for doing all kinds of interesting things with your concurrent programs. Databases and operating systems are another area where people have been doing some interesting and I think creative applications of transactional memory. So this is a recent, I think it was a Eurosys paper, where they're looking at in-memory databases. So the idea here is that rather than doing a standard two-phase locking the way most databases do, so most databases, the truth lives on the disk. And classical database people are all about shipping things between memory and disk efficiently. When you're talking about in-memory databases, things change because you no longer have enormous disk latency to hide your sins. And so you need to worry a lot more about smaller performance issues that you could have ignored earlier. So the premise of this paper is instead of using two-phase locking, we're going to use speculative hardware transactions. And but you can't do it naively. You can't just say, okay, I'm going to take this database transaction and put begin end hardware transaction around it. For all the reasons we've discussed before. It's too big and it's too long and so on. And in particular, we need to keep the hardware read and write sets small because things have to fit in caches. And we need a non-speculative fallback in case we exhaust, in case nothing that we do actually works. And so I won't kind of go into the details, but this is the way that they break things up. They have an idea similar to stack track, where you take the transaction and you break it up into chunks. You execute the chunks in terms of as the hardware transactions. You differentiate it between reads and writes in a more fine-grained way. But it's all a very kind of clever application of these small hardware transactions to speed up your database transaction. And so the takeaway here is that you can take not just concurrent applications the way we were talking about before, but you can take database transactions, carefully break them up into a small hardware transactions. They associate hardware transactions with latches, which is a database speak for mutex locks. And then you use certain kind of validation techniques to glue them together. So when you finish one, you validate, make sure that everything is okay before you move on to the next level. And again, this seems like a kind of technique that could be applied to lots of other things as well. It's non-trivial figuring out how to do this, of course, but it does seem like it's something that is a promising area if you're looking for new research topics. Another approach is to look at specialized kinds of databases, online transaction processing. So again, this is in-memory database, where we're not concerned with shipping things to disks. As far as we're concerned, in-memory is permanent enough for our purposes. And here too, the challenge is how do you keep your memory transactions small enough so that they'll commit. So here, everything you change in the course of your transaction has to fit, in this case, in the L1 cache, because you're using Intel's Haswell. And so a lot of the effort in this paper is to focus on the B tree or hash tree implementation. So it's how to take these data structures that are common to OLTP databases and optimize them so that they work well with hardware transactions. And again, that means making sure that you don't have false conflicts in the cache, making sure that everything fits in the cache, validating that, that they work. The basic idea is that when the database executes, there's a read phase and a write phase. So you read everything as you go along, you buffer your writes, so you don't actually let anybody see the things that you're writing. Then you validate, you make sure that actually what you read was consistent, and if it's consistent, then you bless it and let it go out. And by clever use of metadata, you can make sure that the cache footprint is sufficiently small. So here too, this is an application of hardware transactions that we never dreamed of back when this sort of thing was invented. So takeaway is you can take database transactions, split them into multiple speculative pieces. If you're careful about the order in which you would do reads and writes, and you kind of validate what happens in between each step, then you can get all the advantage of fast hardware synchronization instead of using clunkier software synchronization. Now it seems to me, again, if you could do this with OLTP database transactions, you could probably do it with lots of other applications as well. And each application has its own particular demands and its own particular structures. But again, I think that there is a lot of potentially interesting work that could be done in this way. So here is a sort of a non-database, but a storage system, single-threaded. So here they're using hardware transactions not even for synchronization, but as a kind of a sandboxing. What they want to do is they want to make fine-grained updates persistent. That is, they want to make sure that they last in the presence of failure. So what they do is they take basically the C++ transaction keyword, and they go in and they semi-automatically add instrumentation on the writes. After they commit, they persist the changes to disk. And the idea here is that if something goes wrong, you want to be able to roll things back in an efficient, automatic way, but that's exactly what hardware transactions do. If you misspeculate in some sense, the hardware will clean things up for you. So you don't have to write a complicated software to do this. There are other papers that I'm not going to go into that have also looked at transactional models for other kinds of sandboxing. So you download some JavaScript from the web and you run it and tries to reformat your disk. Then you can detect that and use transactional machinery to roll everything back. So you don't have to keep track of specifically everything that happens, because the built-in machinery will do that for you. This is a recent M.I.T. master's thesis. The idea there is, if you look at Linux, in principle, hardware transactional memory seems like an ideal way to get around all those annoying and expensive kernel locks. So you want to read and write memory. Most of the time there's no conflict, but you need to fire those big semi-monolithic kernel locks anyway, because maybe there is a conflict, and that would be tragic if you had some kind of inconsistency. So in principle you could say, well, in fact, we can do this with hardware transactions. So optimistically we go ahead and we do reading and writing without acquiring the kernel lock. If there's no conflict, then we win. If there is a conflict, who cares? We just roll it back. And if there's a lot of contention, we can go back and get the lock anyway. In fact, this doesn't work very well because the transactions hardly ever commit. And the reasons have to do with complicated aspects of the transaction look-aside buffer protocols. And so by making changes to the TLB protocols, they were able to get this idea to actually work fairly well. But it's not a magic bullet. You can't go in and plug in hardware transactions and have everything instantly speed up. It requires careful thought and a master's thesis worth of work to get this sort of thing to work. But on the other hand, the next time somebody tries to do something like this, I bet it will be a lot easier, because we've seen it before. Data structures. So here, the idea is that if you have a data structure, you can often split the operation into two phases, a little bit like an OLTP transaction. Planning phase, you read a bunch of stuff. You can either read it inside a transaction or just take your chances and read it a potentially inconsistent state of the world. Then you start a hardware transaction, validate that what you read is actually correct. And if so, then do something. Your test for validation can be application dependent. You can sometimes compose these, sometimes not. That's a complicated subject. But the idea is that any software that you have that splits naturally into kind of a reading phase where you decide what you're going to do, and then a phase where you actually do something, is a natural candidate for using hardware transactions, especially since if you can be clever about how you validate the second step. Modern databases use lots of latches. The problem with latches is they tend to be, like locks, they tend to be really complicated. And they're kind of an invitation to buggy behavior. They are also slow because they use a lot of cache coherence traffic. You can take each latch, which you can think of as a critical section, and replace it with a hardware transaction directly. And in this particular case, they found that it worked okay. But they got much better performance by basically doing kind of global rearrangement of things. So in this case, semi-automatically turning critical sections into transactions was not a disaster, but they did much better by a redesign. And figuring out how to make these kinds of redesigns to make algorithms, data structures friendly to transactions is another area that is crying out for further work. Okay, so you see it's time to wrap up. So every new idea in computer science goes through something called the Gartner hype cycle. So somebody invents something. Garbage collection, virtual memory. Now you can do something you couldn't do before. People learn about this and they say, whoa, this is really going to change the world. This is going to pay my mortgage and wash my car and institute near a permanent world of peace. Then they say, wait a second, there's complications. You may have solved some problems, but you replace them with other problems that are actually harder because we never thought about them before. I feel so exploited because I believed in you, and now you tell me that we have even more work to do than we did before. Then gradually people start publishing papers fixing things and improving things little by little. This is what's called normal science. And eventually, kind of like virtual memory, the idea kind of enters the, reaches a level where you can use it, but you never notice it anymore. I mean, you hardly ever think about the fact your laptop has a virtual memory. In the old days when they had big boxes next to my desk, when it would start paging, it would shake like a washing machine. But it's really hard to get your machines to do that now. And so what happens is that my prediction is transactional memory will go through the same cycle. Let you figure out for yourselves where along the curve we are today. So bottom line is this transactional model of computation is here to stay because it's already infected programming languages. It's entered the hardware, basic hardware architectures, x86 architecture, IBM's 3 distinct IBM architectures. So it's not going to go away, and what we need to do is to figure out what to do with it. And what I've tried to emphasize here is sort of not kind of the straightforward, obvious ways of using a transactional memory, but to focus on what I think are kind of creative, non-orthodox approaches. Some of them are probably doomed to failure because they're too crazy. Some of them could be important. But in particular, a lot of these ideas are kind of tip of the iceberg. And I think there's a lot of additional work that could be done to explore these things. And if you're a student, a new student looking for a research area, then I think there are lots of low-hanging fruit here. And I encourage you to look into these issues. So I think we can use transactions as an excuse to rethink just about everything that we do in concurrent systems. Okay, thank you, and I can take questions. Yes?
I'm curious, so in order to really use transactions, they have to make it into compilers, I think, so that they're automatically generated. Do you know of any work in IBM or Intel where they actually do that?
So one thing that Intel does is what's called lock elision, where they will take you write a critical section with a lock, and they will transform it into a speculative transaction, try it once or twice. So to that extent, it's automatically inserted. Whether you can take a program that's written without explicit annotation and add transactions is really kind of a programming language's compiler problem. And you can do that in software as well as in hardware. And I think it's an open question. Right now, you really kind of need to annotate, say, I need this to be atomic, I don't need that to be atomic. And reasoning about that is non-trivial.
So the instructional implementation of transactions, I'm assuming, isn't an actual atomic instruction like a test and set. It's, like you said, optimistic, and then you detect whether or not there's conflicts. Is that good enough to actually implement locks with?
So the instructions are it says start transaction, and it's a little bit like fork or vfork in Unix. You get back a code saying, this is the first time we're executing the transaction, or no, you tried it and it failed, and we rolled everything back. You can certainly implement lots with that, but you're still left with the problem that on contemporary architectures, there's no guarantee about ever succeeding. So you always need to have some kind of a fallback. There are proposals to make stronger guarantees, saying that if there's no synchronization conflict and you fit things in a small enough footprint, then we guarantee it commits. AMD actually had a proposal to do this in a project that ended up being canceled when AMD started running out of money. But my prediction is that future hardware architectures will give you stronger progress guarantees than the no guarantee whatsoever that you get right now. Yeah.
So you talked about the longer transactions. I mean, if the transactions are very long enough, so you're kind of falling back. So it's like falling back to a certain checkpoint, or you're falling back to the start of the transaction?
You fall back to the start of the transaction. There's no way to do checkpoints in current architectures. IBM, one of the IBM architectures has something where you can suspend a transaction, do some non-transactional reads and writes, and then resume the transaction, which is good for performance monitoring and certain kinds of optimizations. But for example, the Intel, you basically take a checkpoint when you start the transaction, and that's the only checkpoint that you have. If you want a later checkpoint, then you have to commit the transaction and restart.
I'll ask another one. Do you think there is a need to extend hardware transactional support beyond a single chip?
Oh, yeah, that's an interesting open question, because most of these, both the Intel and the IBM architectures are based on cache coherence. And once you go into multi-socket, then cache coherence gets harder and harder. And a lot of people predicted that we're eventually going to have to give up on cache coherence. And so there are papers describing how to do hardware transactions without using cache coherence, basically based on logs. The logTM work at Wisconsin was the first, and there's been more recent work. But none of these have been really tried in practice. So what happens to hardware transactions when you scale to lots of chips is basically unknown.
Okay, thanks again.